And we're going to move on now to Holly Christenson, constraining the underdensity with the opacity-density relation at redshift less than 6.
Okay. Thank you for that introduction. Oops. Oh, I'm on the wrong slide here. That's embarrassing. All right, thank you for that introduction. I wanted to get started by placing my work in a broader context, namely that there's a growing number of observations that point to a late and fast reionization. So just as a quick overview, some of those are the cosmic microwave background constraints, which place a midpoint of reionization at redshift of about 7.7. The drop-off in the fraction of galaxies that emit Lyman-alpha, it ratios greater than 6, which gives us a constraint on the neutral fraction, that and the dark pixel constraints we were hearing about earlier. The mean free path measurement at redshift 6, which we've also heard about in this session, and a number of observations from quasar sightlines, including the presence of damping wings at redshift 7, which indicates some presence of neutral hydrogen. All of those observations together paint a picture of a reionization that happens mostly between redshift 6 and 8. There is one observation from quasar sightlines that particularly motivates my work. That is the observed scatter in the effective Lyman-alpha opacity at redshifts greater than about 5.5. So here we have a collection of effective opacity measurements from the literature, plotted as a function of redshift, and we can see that the scatter is pretty tight at the lower end of this redshift range, whereas we get to higher redshifts, we start seeing more and more scatter, and in particular, there's some really highly opaque sightlines at redshifts of about 5.7, which correspond to large Lyman-alpha troughs in the spectra of those quasars. And it's not simple to explain why we should be seeing this scattered Lyman-alpha opacity. So the questions that motivate my work are, what causes the observed scatter in Lyman-alpha opacity? And what does the answer to that question tell us about reionization and how it ends? So there are 3 models that have emerged that attempt to reproduce and explain the scatter in Lyman-alpha opacity. So I'm focusing on those 3 types of models. The first is the temperature model, which attributes the scatter to large-scale fluctuations in the IGM temperature. In the temperature model, a highly opaque sightline corresponds to an overdense region, which reionized earlier and has been cooling for longer, making it more highly opaque. The second model is based on large-scale fluctuations in the ultraviolet background. So in the UVB model, a highly opaque sightline corresponds to an underdense region, which is associated with a suppressed ionizing background. And the third possibility is this ultralate reionization scenario, which we've heard about from a couple other speakers in this session, in which reionization is still ongoing at redshift 5.7 or so and lower. And in this scenario, a highly opaque sightline corresponds to a region of a neutral island of hydrogen that has not yet been reionized. So each of these models makes a robust prediction for what we expect to see in terms of density associated with the highly opaque sightline. And I've just included this figure as an example. This is from the UVB model. The grayscale color bar indicates the effective opacity, and the colored points indicate the positions of Lyman-alpha emitters in the simulation. They're color-coded by their narrowband magnitude. These blue and red circles indicate regions of particularly high and low opacity, respectively, and those illustrate the prediction for density that I've described here is that this blue region, this blue circle, picks out a marked underdensity of Lyman-alpha emitters, whereas the opposite is true for a transmissive region. So given that these 3 models make sometimes opposite, sometimes not, predictions for the relationship between density and opacity, I want to test them out observationally. And the way that we do that is by characterizing the density associated with these highly opaque and highly transmissive sightlines. So I do that by using Subaru Hyper Suprime-Cam to select Lyman-alpha emitters in fields surrounding particularly extreme quasar sightlines. So our program includes 4 quasar sightlines, 2 highly transmissive sightlines, which you can see here are the top 2, and 2 highly opaque sightlines, the lower 2. And you can see in those 2 highly opaque sightlines, there's a very clear Lyman-alpha trough. I've also overplotted the transmission filter curve for the narrowband filter that we use to select Lyman-alpha emitters in these fields. That corresponds well with the Lyman-alpha troughs that we see in the lower 2 spectra. And that's one reason that we opted to use Hyper Suprime-Cam is that it has a narrowband filter well tuned to selecting Lyman-alpha emitters at redshift 5.7. Just as a note, one of the highly opaque sightlines in our program, J148, was previously published as a pilot study for this program by Becker et al. 2018, and has also been followed up by Kishino et al. 2020, so I recommend checking out those papers. The first phase of this program is surveying the two highly opaque sightlines, and we've recently submitted those observations to AppJ, so I wanted to share with you the results from those two surveys. So these two figures show the LAE maps that were selected in these two fields, J148 on the left and J1250 on the right. The colored points indicate the positions of Lyman-alpha emitters that we select. They're color-coded by their narrow band magnitude, and the grayscale color bar in the background indicates the surface density of Lyman-alpha emitters. These two fields are centered on the quasar sightline, which is marked with a gold star, and concentric circles just indicate increments of 10 megaparsecs. There are, just as if you're familiar with the J148 result that's been previously published, this is just a slightly updated version. We've improved our photometry and LAE selection criteria a tad, but fundamentally the result has not changed at all. We still see a clear underdensity of Lyman-alpha emitters in the center of this field, and in the J1250 field, there's also a clear underdensity of Lyman-alpha emitters in the center of the field. The other reason we opted to use Hyper Suprime-Cam is that we get a really large field of view, and so when we're characterizing the density, we're really interested in characterizing the density in the vicinity of the quasar sightline within 10 or 20 megaparsecs and comparing that to the larger field to get an idea of whether it's over or under dense relative to its surroundings. So these are the two clear underdensities that we're looking at. So these two fields provide a nice clear result that we can and do compare to predictions from different models. So these figures show the surface density of Lyman-alpha emitters in each of these two fields as a function of distance from the quasar sightline. And they are normalized to the mean surface density in the field. And in each of these 6 panels, they're compared to predictions from a different model. So for each of these models, the dark line indicates the mean model prediction, and the shaded region indicates the range of expected values. So there are 6 models here. I would like to start by drawing your attention to the two on the left, the upper and lower left. These two models are variations on the ultraviolet background model, which made a clear prediction that a highly opaque sightline should be underdense, and that agrees well with our results in these two fields. Here on the upper right, we have the temperature model, which predicted that a highly opaque sightline should be an overdensity. That is the opposite of what we're observing in these two fields, and our observations disfavor this model. In the lower center and right, these are two variations on a late reionization model, which made a clear prediction for highly opaque sightlines that they should be underdense, and that agrees well with our observations. So phase 1 of this project has clear results that we are disfavoring the temperature model and confirming these results from a pilot study in a second highly opaque sightline. If we want to take this further and try to understand which, if either, of the UVB and late reionization models are preferred by the observations, we need to move on to phase 2 of this project, which considers highly transmissive sightlines. So we have recently been able to select LAEs in a highly transmissive sightline. So I will show you that, but first I want to comment quickly on the model predictions for the highly transmissive case. The UVB model makes a clear prediction that a highly transmissive sightline should correspond to an overdensity of Lyman-alpha emitters. The late reionization case is slightly less clear. It makes a robust prediction for the highly opaque case, but Monsieur and Deloisio find that a transmissive sightline could arise from a range of possible densities, so there isn't quite that clear-cut transmissive, definitely one or the other. So there's a range of possibilities there. So keeping those model predictions in mind, here are the LAEs that we select in this J1306 field, which is our first look at a transmissive sightline. This uses the same format as before, where it's a map of our LAE candidates, and there are 2 things that are striking about this figure. The first is that there is a pretty clear underdensity in the center part of this field, within 10 or 20 megaparsecs of the quasar sightline. And the second is this large overdensity that is directly adjacent to the center of the field. So this is a pretty preliminary result. It's not immediately clear yet if or how important that large overdensity is, but it's certainly intriguing. Taking at face value, these results disfavor the UVB model, which predicted that we should be seeing an overdensity in the center of this field. But it's consistent with predictions from the late reionization model, which allowed for a broader range of possible densities. Like I said, it's not entirely clear yet how to interpret this, but one possible interpretation that is interesting is that this highly transmissive sightline is showing us a region that has been recently reionized, potentially by all of the ionizing sources that are present in this large overdensity. So with that, just to conclude, we've confirmed the association between highly opaque sightlines and underdensities in 2 fields now. And our first observation of the transmissive sightline are pretty interesting. They show an underdensity that at face value disfavors the UVB model, and it's consistent with predictions from the late reionization model. So I'll leave you there.
Thank you, Holly. Very nice talk. We'll wait a little bit for questions.
All right, so that's the first question. How do you distinguish between a real deficit of galaxies and a bunch of galaxies which have not been able to ionize their surroundings yet?
That's a great question. I mean, I think an interesting or an important thing to mention is the other authors that have looked at this sightline, Casino et al. 2020, were interested in kind of the same question. So they looked for continuum selected galaxies, and they published a selection of continuum selected galaxies in this field, which we wouldn't expect to be suppressed by neutral hydrogen. So the J148 field, they're able to reproduce the deficit of galaxies we find in the J148 field, and we actually have some additional data from Subaru to make that selection ourselves, and our preliminary results are consistent with the same thing. We also reproduce our underdensity of galaxies, so that's been an important kind of check in our work to verify that the void we're seeing is real.
While we're waiting for other question, okay, another question came in. Said I may have missed, but why is the UVB model disfavored?
So the UVB model predicted that a highly transmissive sightline should correspond to an overdensity, so it's nearby a lot of ionizing sources, and that is not what we're seeing here in the J1306 field. So this prediction is specifically for really close to the quasar sightline. I guess I can show you the predictions here. So this is for the highly opaque models, but just to give you an idea of what these predictions look like, you expect to see, we're interested in like a differential measurement where we're comparing the very inner part of the field to the rest of the field. So that inner 10 to 20 megaparsecs is really where we're making this comparison. So for example, in the highly opaque sightlines, we see these models predict a deficit of LAEs in the inner part of the field, and then it comes back up to the average. So coming back to this result in the J1306 field, we see this pretty clear deficit in the very central part of the field. And at least at face value, that's not consistent with what the UVB model predicts, which is that we should be seeing an overdensity in this part of the field.
Okay, so another question about the UVB models. So in those models, what is the variance between overdensity and opacity? For example, if the UVB model was right, how unlikely is it to find an ionized region that is not overdense?
That is a great question. I'm not sure that I don't happen to have detailed predictions from the UVB model to hand right now. This is a pretty preliminary, this result's pretty preliminary, but that is a great question, and I will definitely jot that down to follow up on.
Okay, looks like you have a couple other comments in the Slack, but thank you very much again, Holly. In the interest of time, we'll move on.